In this segment, I'd like to introduce you to some large sample theory that will be useful throughout the course. For background reading, you could see, take a look at Davison's statistical models. Pages 28 to 37 on convergence is good, and pages 77 to 90 is a pretty deep treatment of simulation that is going to be that is more intense than what we're doing, and you should at least take a look at it. The overview of what we're going to do is some foundations of probability, the law of large numbers, consistency of statistical estimators, the central limit theorem, convergence of random vectors, and finally the delta method, which allows us to calculate the convergence of functions of random variables and random vectors. We'll start with the sample space, capital Omega, with a little omega in big omega. It's a set. It's omega is a set. It's the underlying sample space. It could be a set of eggs in a warehouse, and it could be, or literally the universe of websites from which we intend to sample. Script F is a class of subsets of omega, probably a sigma algebra. If omega were countable, script F could be the class of all subsets. And there's a probability measure, P, defined on the elements of F. And so, for example, maybe each website is equally likely to be chosen with replacement. And random variables are functions from omega into the set of real numbers or into vectors. So you really could think of X as a measurement, and if the elements of omega were eggs, then X could be the weight of the egg. And the probability that X is in some set B is just really the probability of the set of omega, the set of eggs, such that the weight of the egg is in B, so that the probability distribution of X is referred back to the original probability distribution on the elements of this foundational set omega. A random sample, one can have a random sample that is a collection of independent and identically distributed random variables x1 through xn, where n is the sample size, and they're all functions of omega. Calculate a statistic t, which is a function of x1 through xn, and t is also a function of omega, and we'll use t subscript n to indicate that it's depends on the sample size. Letting n go to then we can let n go to infinity to see what happens for large samples. We're going to discuss three modes of convergence in this class: almost sure convergence, convergence in probability, and convergence in distribution. And we'll start with almost sure convergence, and we'll say that Tn converges almost surely to T, and write Tn goes as almost surely to T if the following condition holds. That is, if the probability that the limit of Tn is equal to T, if the set of omega such that this limit holds, thinking of each omega as a little fixed element right now, like a fixed quantity, if the probability of that set of omega equals 1, then we'll say that Tn converges almost surely to T. This is the most advanced form of convergence, and at the same time it's often the easiest to deal with, which is why I like it, because it obeys all the rules that you're familiar with of ordinary limits, and you can just do all the things that you usually do, L'Hopital's rule, and the continuous mapping, and the limit of a product is the product of limits, and everything that you're used to, and then at the end just say, well, except possibly on a set of probability 0. And all the usual rules apply. It's called convergence with probability 1, or sometimes strong convergence. In this course, the convergence will usually be to a constant rather than to another random variable. That is, it'll be to a constant random variable. A sort of a target. Tn is often some kind of a statistic, and the value that it's going to see is some constant. The strong law of large numbers is you let x1 through xn be independent with common expected value mu, and then it just says that the sample mean goes almost surely to that common expected value. And the only condition required for this to hold is the existence of the expected value itself, even though it's sometimes proved under conditions of finite fourth moments for relatively medium grade classes. But the real thing doesn't require the existence of fourth moments. It only requires the existence of that common expected value mu of the target. The idea that probability is long-run relative frequency, which is what the frequentists believe, is justified by the strong law of large numbers. So you've got a statistical experiment with a probability of success, theta, and you carry out the experiment many times independently, coding the results xi equals 1 if it's a success and 0 if it's a failure. And then the sample proportion of successes converges to the probability of success because the expected value of xi is just the x, right, against the multiplied by the probability of x, but x itself is only 0 or 1, so that's 0 times 1 minus theta plus 1 times theta, which is theta, so that the expected value of this Bernoulli random variable is theta, and the relative frequency is, well, you simply add up the x's, but the x's are 1 if it's a success, so the sum of x is just the number of successes divided by the total number of trials, which is the relative frequency of successes, and that's x bar, which by the law of large numbers, the strong law of large numbers, goes almost surely to theta, and that justifies thinking about probability as the relative frequency of some outcome in a large number of independent trials. The law of large numbers justifies using simulation to figure out hard probability problems by computer. Like what's the probability of a hurricane, or you can estimate almost any probability that's hard to figure out. Statistical power is often difficult, and if it's difficult enough, you can resort to simulation. Think of a big giant weather model where you're trying to predict whether it's going to rain or not, or whether the temperature is going to dip below the frost point. You have a model with a large number of parameters based on physics, and with random components, who knows, maybe even Brownian motion, and you run the model over and over and over again, which is why they use supercomputers, and get the relative frequency of rain or a hurricane and give it a probability, an estimated probability. Performance of statistical methods can be investigated this way. And of course, whenever you do this, you need confidence intervals for the estimated probabilities, and that comes with, so that you get not only an estimate of a probability, but a confidence interval around it to give you an idea of how much uncertainty there is in the estimate. Here's an example of estimating power by simulation. We'll just do that same toy example we did for the coffee taste test. If you remember, there were two test statistics for testing the null hypothesis that theta equals theta 0, the Z1 and Z2. And when theta is not equal to theta 0, calculating that probability, that's the power, the probability of that the absolute Z2 is bigger than the critical value, can be challenging. I say this even though we did it in the first lecture, but we did it with a quick little sleight of hand. I kind of cheated you a little bit, and there was a thorny point that I didn't mention. But I did it. It gave the right answer, but it was not altogether honest of me. Because there was a tricky little part that I just hand waved away instead of dealing with it honestly. But we can get it by simulation as follows. So here's a strategy for estimating statistical power by simulation. You generate a large number of random data sets under some alternative hypothesis of your choice, And for each data set, you test the null hypothesis. The estimated power is simply the proportion of the times that the null hypothesis is rejected, period. How accurate is the estimate? Yeah, p hat plus or minus. This is just a large sample confidence interval for a proportion, and so it's very straightforward. The maybe generating the large number of random data sets under the alternative hypothesis, that might be a little bit troublesome. It's a little bit of coding anyway, but this approach works very well for a variety of problems. Just as an example, testing that null hypothesis that theta equals 0.5 when the true theta was 0.6 and n equals 100. The power of Z1 we found was about 0.52, and Z2 has got is this formula. So in order to get the power, I first set the seed on the random number generator. In case you don't know, the random number generator in R and most other softwares is really a very, very long stream of numbers between 0 and 1, and it's deterministic. It's if you start someplace in the sequence, eventually you'll get back to where you started, and then the sequence will start to repeat. In the case of the random number generator used by R, that time when the sequence, if you constantly are generating random numbers with a very robust computer, the time when it repeats will be well after the end of the universe. So it's a very, very long sequence, but the seed of the random number generator essentially determines a starting point so that you can always get exactly the same numbers next time you run the simulation, something that's very useful for debugging code. So I use a random number seed a lot of the time. I chose m equals 10,000 for my Monte Carlo sample size, and then tried theta equals 0.6. We're testing the null hypothesis, theta equals theta 0 equals a half, and n equals 100. Calculate y bar, which is just a binomial random variable, and divided by n. Yeah, so that's like the number of successes, right? That's quicker than generating the Bernoullis, and it is a vector of length m, because you're generating m of them. So now you've got y bar, you've got m y bars, and then when you calculate Z2, and here's just the straight formula for Z2, which is above there, it's another vector of length m, and then the power is just the length of the vector Z2 such that its absolute value is bigger than 1.96, and divide by m, and the power is estimated to be 0.5394, which is not very far off from the power of Z1 either. Margin of error, it's just this large sample confidence interval, and I calculated margin of error. The power, by power I meant estimated power, and that's my p hat, and the margin of error was 0.01, and so the lower confidence, it's a 99% confidence interval, right? Why not have a higher than usual confidence in these simulation examples, since sample size is so cheap? The lower confidence limit is the estimated power minus the margin of error. The upper confidence limit is the estimated power plus the margin of error, and we get a confidence interval from about 0.53 to about 0.55. So here's more simulation. Recall the change of variables formula. This is something that came up in the zipper example, but I didn't introduce it formally. You've got y equals g of x, and one way of writing the expected value of y is to just integrate y against its density. But you can also get the same answer, says the change of variables formula, by integrating the function g of x against f of x. This is a very big theorem, and it applies under the most general possible circumstances. Or for discrete random variables, the integrals are replaced by sums. And yes, again, it's a big theorem, not a definition. So here's an example of applying the change of variables formula to approximate some expected value of g of x. The way you do it is as follows. You simulate a random sample from the distribution of x, calculate what's really essentially a sample mean of y's. Yeah, that's because that's what it is, because y equals g of x. And that goes almost sure, by the law of large numbers, goes almost surely to the expected value of y, which is the expected value of g of x. And so, for example, you can approximate the expected value of x to the k by raising the individual simulated xi values to the power k, or even multidimensional things like the expected value of u squared times v times w cubed is, again, might be very, very difficult to do analytically, and yet you can do it you can get an approximate numerical value very easily with the law of large numbers. So yeah, so it's not just approximating probabilities with simulation, it's approximating expected values. Sample moments converge almost surely to population moments. Here's a nice trick, and I believe that this is Monte Carlo integration, which I believe was invented by somebody in the Manhattan Project during World War II when they were busy working on the atom bomb, and I believe that they had something like a difficult 8-dimensional integral that they couldn't really do analytically, and somebody thought of just using the law of large numbers and doing it by what was at that time the most sophisticated computer in the world, which was much less powerful than the old PCs that are getting thrown out on trash collection, and much less powerful than your cell phone. But in general, yeah, and I don't think the person even published it either because it was too obvious. But it's a very handy trick. So the idea is that you want to approximate the integral of h of x, where h of x is some nasty function. And so let f of x be a density, and you want to make sure that f of x is bigger than 0 whenever h of x is not 0, so that there's a so that f of x kind of covers the range where h of x is difficult to deal with. Then you can write the integral of h of x and simply multiply and divide by f of x, which is why you want f of x to not be 0. And that's just the expected value of the function h of x over f of x. So how do you do that? It's the expected value of a g of x. And so you sample x1 from xn from a distribution with density little f, and then calculate these yi's equals g of x for I equals 1 to n. Calculate y bar. It goes almost surely to the expected value of y, which is the expected value of g of x, which is exactly the integral that you want. And a confidence interval for mu equals the expected value of y is routine, because the confidence, there are lots of, every statistics book has got a formula for the confidence interval for a mean, so there's no problem. This can be extremely handy, especially when the function is very nasty, or it has a multi-dimensional integral over a funny boundary. This is very nice. Okay, so that's almost sure convergence. Convergence in probability has got the following definition. So there are 3 modes of convergence, right? Almost sure convergence. Well, there's more than 3, but we're going to talk about 3. There's almost sure convergence, there's convergence in probability, and there's convergence in distribution. And we'll say that Tn converges to a random variable t in probability, and write Tn going in probability to t if for all epsilon bigger than 0, the limit as n approaches infinity of the probability, always of the set of omega, such that Tn minus t, that's the distance between Tn and t, is less than epsilon, is equal to 1. That is to say, you've got a little margin around t of omega, and as long as the limit of the probability, a little band, if you will, where Tn and t are very close, and as long as in the limit the probability that Tn the probability distribution of Tn is very close to t, as long as that probability is extremely high and gets higher and higher as the sample size approaches infinity, then we'll say that Tn converges in probability to t. For us, it's a little easier because usually the convergence is to a constant, and now what we have is a little epsilon interval around this constant c, and we're saying that in the limit all the probability distribution of Tn gets into that little interval. Contrast this with almost sure convergence. There we're saying that it's the probability that the limit of Tn equals c is 1. And here we're saying the limit of the probabilities equals 1. The meaning of it is that no matter how small the interval is around c, if you take n large enough, that is for all n bigger than n1 or something, the probability of getting that close to c is very close to 1, as close to 1 as you like by taking n large enough. And in this class, we'll seldom use this definition directly. The weak law of large numbers simply says that the sample mean converges in probability to mu, that is that common expected value of x1 through xn. And almost sure convergence implies convergence in probability in general, so that the strong law of large numbers implies the weak law of large numbers. Often, people don't even distinguish whether they're talking about the strong or the weak law. Frequently, they're talking about the weak law because convergence in probability is kind of technically easier to deal with. The definition is easier to use, but on the other hand, the mechanics of using convergence in of using almost sure convergence are quite easy because it's ordinary limits. Here's the concept of consistency, something that I brought up in the zipper example, and I hadn't defined yet. T is a statistic estimating some parameter theta, and the statistic T is said to be consistent for theta if the estimator converges in probability to theta. That is for all theta in the parameter space. That is to say, the limit as n approaches infinity of the probability that Tn minus theta in absolute value is less than epsilon, that is that Tn is really, really close to theta, in the limit that probability equals 1. And the statistic Tn is said to be strongly consistent for theta if Tn is going almost surely to theta, and of course strong consistency implies ordinary consistency. I just want to point out that consistency is great, but it's not enough. All it means is that as the sample size becomes indefinitely large, you probably get as close as you like to the truth, but it's the least we can ask. And estimators that are not consistent are completely unacceptable for most purposes, which actually is one of the main reasons for bringing it up in this course, because it's the failure of consistency that will reveal that there's a really serious problem, maybe with a statistical model under some circumstances or with some applications. So check consistency, and if it's true, all you can say is, well, okay, great. And if consistency fails, then there's a real problem. In general, Tn goes almost surely to theta consider this example. So Tn goes almost surely to theta, and we'll define Un to be Tn plus 100 million divided by n. Well, that goes almost surely to theta too, because just like an ordinary limit, this second term goes to 0 as n approaches infinity, but for any practical purpose, Un is terrible. So this is a kind of quick toy example that shows you that consistency by itself doesn't mean good estimation at all. It's just that lack of consistency usually means bad estimation. As an example, consider the consistency of the sample variance. Okay, let's define sigma hat squared n. This is the estimated, the estimate of a variance as a sample variance. And if you don't mind, I'd like to divide by n instead of n minus 1 because I don't care if it's unbiased. But but you'll see that with a n in the denominator, we get things that look like sample means. So expanding the square and distributing the summation sign, that is, this quantity is 1 over n times the sum of the xi squares. Oh, look at that. Look at that. That's just the sum of, it's the average of a bunch of g of xi's. So this part is going to go almost surely to the expected value of x squared minus x bar squared. And you know that x bar goes almost surely to the expected value of x, say, call it mu if you will. And by continuous mapping, that x bar squared is going to go to mu squared almost surely. That is like an ordinary limit, except possibly on a set of probability 0, which we can disregard. So by the strong law of large numbers, that is what I've been saying, x bar goes to mu, and this part, this 1 over n times the sum of xi squares, goes almost surely to the expected value of x squared, which is sigma squared plus mu squared. Yeah, because sigma squared is equal to the expected value of x squared minus the expected value of x squared. And then because that function g of xy equals x minus y squared is continuous, this sample variance is the function g of these two sequences of random variables, if you will. That goes almost surely to g of the targets, sigma squared plus mu squared and mu, which is just sigma squared plus mu squared minus mu squared equals sigma squared. And we've shown the consistency, the strong consistency of the sample variance with no conditions on the distribution in question, except that the variance itself exists. Third mode of convergence is convergence in distribution. It's sometimes called weak convergence or convergence in law. And so take a sequence of random variables and denote their cumulative distribution functions by f1 of t, f2 of t, and so on, respectively, and the cumulative distribution function of the target t by just f of t without any subscript. And then we'll say that Tn converges in distribution to t, and write Tn goes in distribution to t. Usually now, in our applications, t is really going to be a random variable and not a constant, though sometimes it's a constant. Mostly it's a random variable. If what? If for every point t at which f is the target cumulative distribution function is continuous, we have the limit of the cumulative distribution functions equals the distribution of the target. So convergence in distribution really refers to not so much the convergence of the random variables themselves, but the convergence of their cumulative distribution functions, and you can disregard any points at which the target is discontinuous. And there are a lot of fun homework problems about this in other classes, but not in our class. Again, we're not going to use this definition directly very much. Instead, we'll just just in the case of convergence of in probability and convergence almost surely, we'll mostly start with the law of large numbers, and when we're doing convergence and distribution, mostly we start with the central limit theorem. The univariate version of which goes as follows. You let x1 through xn be a random sample from a distribution where the expected value mu and variance sigma squared, and then Zn, which is, well, you take x bar and subtract off its expected value and divide by its standard deviation, converges in distribution to a random variable z, which is normal 0, 1. This is the standard way of writing the univariate central limit theorem. And this is convergence in distribution. And now the connections among the modes of convergence are that if Tn goes almost surely to T, then Tn goes in probability to T, and that in turn would imply that Tn will go in distribution to T. So it goes in one direction, sort of downhill, if you like, from the strongest form of convergence to the weakest. And if A is a constant, then convergence in distribution to A implies convergence in probability to A, which is not too hard to prove if you're in that kind of class. But it doesn't imply anything about convergence in, it doesn't imply anything about almost sure convergence at all. Now, sometimes we say that the distribution of the sample mean is approximately normal or asymptotically normal, and that's justified by the central limit theorem. But it does not mean that x bar converges in distribution to a normal random variable, not at all, because the law of large numbers says x bar converges almost surely, and thus in probability, to a constant, mu, the expected value of the normal distribution. And so x bar must converge to mu in distribution as well, and not to a normal distribution. So why would you say that for large n the sample mean is approximately normal mu sigma squared over n? It's for this reason. Suppose you calculate, you've got a random sample from some unknown distribution, and you calculate Zn equals square root of n times x bar minus mu over sigma, and we know that that converges in distribution to a normal 0, 1. That's the central limit theorem. So let's consider the probability distribution of x bar, or anyway, its approximate probability distribution for large samples. So what is that? That's the probability that, so what did I do? I subtracted mu from both sides, and then I multiplied both sides by the square root of n, and then I divided both sides by sigma. And that, on the left side, we have Zn, which is approximately standard normal. And so then this probability is approximately phi, the cumulative distribution function of a standard normal, evaluated at the square root of n times x minus mu over sigma. Something that you could figure out with a table of the normal, with a table of the normal distribution. If you had R or or if you had time. But then on the other hand, suppose that some random variable y is exactly normal mu sigma squared over n instead of approximately. Then the probability that, looking at the cumulative distribution function of y less than or equal to x, again, I'll do exactly the same machinations and subtract mu, multiply by the square root of n, and all divide by sigma and all that stuff. And that's the probability that Zn is less than the square root of n times x minus mu over sigma. The same probability we've got there, and that's not approximately. It's not approximately. It's exactly the cumulative normal distribution function evaluated at square root of n times x minus mu over sigma. So this means that in practical terms, if you're figuring out probabilities, you would do it in exactly the same way for x bar that you would do for a random variable that really was normal with these parameters. And so that justifies saying that, well, that that's the sense in which x bar has an approximate normal distribution, because if you were calculating probabilities using the central limit theorem, you would do it the same way as if it was exactly normal. Now, what we've been doing up till now is all scalar, but all the definitions that we've seen and all the basic facts are the same regardless of whether it's a single valued random variable or a random vector, a vector of random variables. So again, almost sure convergence. In all these definitions, the boldface quantities are in Rm unless otherwise stated. So now we've got an m-dimensional vector of random variables converging to an m-dimensional target, and it means it's exactly the same definition that you would have had for the scalars. For convergence for strong convergence almost surely, that is, convergence in probability, and convergence in distribution, it's exactly the same thing, except that everything is vector valued. Again, you have almost sure, for vectors, you have almost sure convergence in implying convergence in probability, which in turn implies convergence in distribution. And if A is a vector of constants, you've got this partial converse where the convergence in distribution then implies convergence in probability to that vector. You've got the strong law of large numbers. x1 through xn are now each m-dimensional random vectors, and they've got a finite first moment, and x is a general random variable from the same distribution. Then x bar is also m-dimensional. It's a vector of sample means. Converges almost surely to this. This is a constant, a vector of expected values. And there's a central limit theorem, which says that if x1 through xn are independent and identically distributed random vectors with expected value mu, and instead of a variance covariance matrix sigma, then square root of n times x bar minus mu converges in distribution to a multivariate normal with mean 0 and covariance matrix sigma. The difference between this is another version of the central limit theorem, in which in the univariate version you've got a divided by sigma in the sequence of random variables itself, and in this version it's the target that's not anything like a standard normal. It's got mean 0, and its variance covariance matrix is sigma, the variance covariance matrix of the original random variables, and it's just more convenient to state this way because it's not so easy to put sigma in the denominator of vector valued functions. This is part 1. Part 2 are Slutsky theorems for convergence and distribution. The first one is basically continuous mapping, and it's okay to refer to it as continuous mapping. So you've got Tn, is in random vector. Tn is in Rm. We're going to have to talk about random vectors pretty soon. Um, and if so Tn is converging in distribution to some random vector t, and if this, and there's a function of f, which is a function mapping Rm into Rq, like the original random vectors might be 6-dimensional, and Q might be 2-dimensional, where Q is less than or equal to M. And this function has got to be continuous, except possibly on a set C with the probability T of the T is in C, the target is in C is equal to 0, then f of Tn goes in distribution to f of t. So this is just ordinary continuous mapping, except that it allows for some points of discontinuity of the function, as long as those points of discontinuity have got probability 0 under the target distribution, not necessarily under the distributions that are tending toward the target. Second one is handy, which is that if Tn is going to T, and if the difference between Tn and some other sequence Yn is going in probability, not distribution, to 0, then, well, convergence in distribution to 0 would imply convergence in probability to 0 because of that partial converse. So forget I said that. Anyway, if Tn is going in distribution to T, and if the difference between Tn and Yn is going in probability to 0, then Yn is going in distribution to that same target. A very handy theorem at times. Trust me. Because sometimes the what you're really interested in is Yn, and you cannot figure it out. But you can figure out Tn, and you can figure out the difference between Tn and Yn, and then you can get what you want, which is that Yn goes in distribution to the target. This last one is what I would call the Slutsky stack-em-up theorem, which is that you've got Tn and Yn, both random vectors, and what you do is you form a new random vector which is of length d plus k by simply stacking the elements of Tn on top of the elements of Yn. And if Tn isn't going in distribution to some random variable t, but Yn isn't going in probability to a constant c, then the stacked Tn over Yn goes in distribution, not probability, to the stacked up T over C. The way it'll go, you'll see examples, is that this will be the first stage, and then the constant C will be something that you might want to divide by, or something like that. And there's a that you will then apply Slutsky lemma or theorem 1 to some continuous function of T and C to get a continuous function of Tn and Yn going to the same continuous function of T and C. Very handy. The Slutsky theorems for convergence in probability follow exactly the same pattern as the ones for convergence in distributions, except that everything is with respect to convergence in probability, instead of some of them being in this last part. For example, the here for example, Tn and Yn. This third part is a little bit different. The Tn and Yn doesn't have to be going in probability to some constant. It's just going in probabilities to some random vector y. So that if Tn is going in probability to t and Yn is going in probability to y, then you can simply stack the Tn's and the Yn's over on top of each other, and they go to the stacked up version of the targets in probability. Very nice. Finally, there's the delta method, which is due to Cramer, and there's a very nice book by Ferguson called An Introduction to Large Sample Theory, which covers this, and that it's from Ferguson's book that I've taken most of these theorems. So what you've got is a function g which maps rd into rk, where k is less than or equal to d, and see this g dot of x? What is it? It's a matrix whose ij element is the partial derivative. See this function g is actually a vector of functions, which takes a function of element 1, element 2, all the way up to element d, and then maps in and gets a target in rk. So you take the partial derivative of function I with respect to xj, which will be a k by d matrix. This is actually a Jacobian, and if the elements of that Jacobian matrix of derivatives are continuous in a neighborhood of theta, then if Tn's a sequence of random variables such that you've got convergence in distribution, this looks like a central limit theorem, doesn't it? Which is the way it usually is applied. So you've got this sequence converging in distribution to t, then a similar version of g of Tn minus g of t goes in distribution not to t, but to g dot, that is this matrix of partial derivatives times t. And in particular, if they're multivariate normal, then the target itself is multivariate normal, and the variance covariance matrix of the target random variable is just this Jacobian times the original variance covariance matrix times the transpose of the Jacobian. Well, this certainly we'll put this aside for a little bit, because it's pretty clear that I need to talk a bit about random vectors and the multivariate normal distribution before we get back to an application of this one. Okay, we're now on slide 34 out of 52 in the large sample lecture, and I believe that our first meeting of this class has come to an end now. So I'm going to stop it here and take it up at this point, and continue, finish off the lecture on the large sample tools in person at the second meeting of our class. The end. Goodbye for now.